In Lecture 4 of our chemistry series, we are going to go into compounds and stoichiometry. When we're dealing with chemical interactions, we have to deal with moles. Moles are simply the quantity of any substance equal to the number of particles in 12 grams of carbon. This is where we get Avogadro's number from, which is a number you're going to have to memorize. When you're calculating the moles of a substance, you take the mass of the sample and you divide it by the molar mass. So if we were to talk about something like sodium chloride, so sodium chloride, NaCl, if we look at it from a weight standpoint, chlorine weighs about 35 and sodium weighs about 23. So sodium is about 23. So if we add these, sodium chloride is going to have a molar mass of approximately 58. So if we have 55 grams of sodium chloride, we divide 55 by 58 to get the number of moles. When you're doing equivalencies and any sort of calculations regarding chemical equations, especially when calculating things like limiting reagents, you have to use moles. Equivalents are simply molecules listed in chemical equations. They are set equal by molarity. So again, number of moles is going to come into play. There are different ways to talk about equivalencies though. There's the gram equivalent weight, which is molar mass over the number of moles. Normality, which is a measure of concentrations in terms of equivalents per liters. And molarity, which is normality over number of moles. So if we talk about normality in particular, an example of this is when we're talking about acidity. If we're looking at the normality of the protons off of acids, we would do it like so. So for example, HCl has only one proton, therefore this would be considered one normal. If we were to look at something like H3PO4 though, this would be 3 normal because it has 3 protons. There are different ways to represent compounds, and this is based on the law of constant composition, which simply states that any pure compound is going to have the same elements in the same ratio. The empirical formula is the smallest whole number ratio of elements in a compound, whereas the molecular formula is the same or multiple of an empirical formula. This is the given formula for a compound. So for example, if I were to have C4H8, this would be a molecular formula, but if I were to reduce this to an empirical formula, this would simply be CH2, because this is in a 2-to-1 ratio. The percent composition is simply the mass of the element in the formula over the molar mass multiplied by 100 to get it to a percent. So if I were to do something like sodium chloride again, if I were to look at the percent composition of sodium, I would take the weight of the sodium, which is 23, and I would divide it by the molar mass, which we calculated earlier as being 58. Now, this is going to be roughly a little less than 50%. Stoichiometry. This is based on limiting reagents, which is the first compound consumed in a reaction. Because of that, it's going to dictate the progression and quantity of the rest of the products in the reaction. So, the reaction can only proceed as far as the limiting reagent allows. Theoretical yield is based on how much you should produce if all the limiting reagent is consumed. However, what you're going to notice is that this is going to be lower in practice than it is in theory. This is because there are other factors that we can't necessarily account for when we're actually running a reaction. These could include air, residual glassware, and obviously operator error. So the actual yield is generally less. When you take the actual yield, divide it by the theoretical, and multiply it by 100, you're going to get percent yield, or how much yield you got versus your theoretical. In general, when you're talking about theoretical and actual, you're going to be using them in reference to the percent yield. In the real world, if you can get a percent yield of over 50%, that's pretty solid. Ions and nomenclature follow various rules, starting with Roman numerals to denote the charge. So an example of this would be if I were to have Fe2+, if I were to see this represented, I would list it off as iron 2. Anything that has the suffix us has a lesser charge, whereas ik has a higher charge. So again, if we were to use iron as our example, Fe2 plus versus Fe3 plus, Fe2 plus would be listed as ferrous, whereas Fe3 plus is going to be listed as ferric. Copper also can follow this, so you've got Cu plus and Cu2 plus. Cu plus being listed as cuprous, Cu2 plus being listed as cupric. Any monatomic anion is going to be listed in the "ide" suffix, so hydride, fluoride, oxide, etc. Oxyanions are based on how much oxygen is present. Now, when we're talking about polyatomics, you have to use the prefixes to denote the quantity as well. So, for example, mon, di, tri, etc. Ionic charges are following in largely familial trends, and those are ones that you're going to be seeing on the MCAT by and large. In general, metals will form cations, whereas nonmetals will make anions. If you remember our second lecture in this series, you're going to remember this information. An electrolyte is something that contains equivalents of ions from molecules that dissociate in solution. So again, if we look at sodium chloride, that's going to dissociate in water to sodium ions and chlorine ions. So it's going to have two electrolytes, quote unquote, in solution. The strength of said electrolytes depends on the degree of dissociation. So for salt sodium chloride, in this example, it's going to have a pretty high strength of electrolyte because it's going to dissociate very quickly. When we're talking about ionic charges, we can look at our family trends. Alkali metals in general are going to have a +1, alkali earths +2. If we go to the other side, we've got noble gases with a 0, halogens with a -1, chalcogens with a -2, and the nitro and phosphorus column in -3. Note that transition metals have been blocked out. This is because the charges on transition metals can vary. The last bit we're going to go into in this lecture are types of chemical reactions. Often, the easiest way to represent chemical reactions is if we were to look at dating. So, the synthesis reaction would be when there's two reactants that form a singular product. So, boy meets girl and boy dates girl. Decomposition is when a singular reactant dissociates into two products. So, couples that break up would be a decomposition. A single displacement is when one substance is replaced for another. So in this example, we've got a couple and boy leaves girl for another girl. A double displacement is when there is a switch of partners. So boy girl switching out for different partners. Other reactions we need to talk about are combustion reactions, which occur with a fuel and an oxidant, and they're going to form water and carbon dioxide subsequently. The oxidant for these is generally going to be just oxygen in the atmosphere. And the last one we're going to go into is the neutralization reaction, which are when there is an acid and a base that neutralize each other and form a salt. Note that with neutralization reactions, water is generally a byproduct as well. We'll finish up there with compounds and stoichiometry. In the next lecture, we're going to talk about thermodynamics and chemical kinetics.